Welcome again to week 8 video PowerPoint lecture, part 2. This part begins our study of chapter 9, which covers solutions. So without further ado, let's begin. So I want you to recall mixtures and solutions. Recall, we studied earlier in the semester matter, and we broke matter down. We looked at matter and we said, can it be separated by physical means? If it could not be separated by physical means, that meant we had pure substances. All right, pure substances, go back and review on your handout in previous PowerPoints. Remember, pure substances can't be decomposed. If they can't be decomposed by ordinary chemical means, that means we had compounds or we had atoms, okay, or elements, okay? On the other end, all right, when we're asking the question, can the matter be separated by physical means? If the answer is yes, that meant we had mixtures, okay? When we're sure that we have a mixture, we then ask the question, is the composition uniform? If the answer is yes, remember we had a homogeneous mixture. If the answer was no, we had a heterogeneous mixture. So we're going to focus on this, and we're coming back in this chapter to focus on, hold on, let me just pull up a color here. Okay, we're focusing on this end of our matter breakdown. Okay, all right. So now where do we go? Whoops. All right. Let's see what we're doing here. Okay. Nope, I don't want a color. Why is it not going? All right. Advance to the next end. There we go. Sorry about that. Okay. It was not behaving for me. All right. So focusing on that end of our chart. Okay. Let's recall heterogeneous mixtures. Okay. Heterogeneous mixtures. Remember, they are non-uniform mixtures. That means they have regions with different compositions in them. On the other hand, a homogeneous mixture is a uniform mixture that has the same composition throughout it. Recall that there was another name for homogeneous mixtures. We called them solutions. Solutions, homogeneous mixtures that contain particles the size of a typical ion or a small molecule. Okay, so there we go. This chapter on solutions is going to focus on that one part of our matter breakdown. Okay, so let's move on. Okay. When we talk about a solution, we have to be familiar with two terms. First term up here, all right, solute, okay. Solute is the dissolved substance in a solution. So how do we know which one is dissolved and which one is not? Okay, the solute is typically the substance in a solution that occurs in a lesser amount. The second part to a solution is what we call the solvent. All right, a solvent is the dissolving medium in a solution. How do we know which is the dissolving medium in the solution? It is typically the substance in greater amount. Examples of each. All right. So if we dissolve, or if we have a sample of salt water, okay, the salt is the solute. It is the substance in lesser amount. So the salt in a salt water solution is considered a solute. Okay. Another example would be if we had soda drinks. Soda drinks, of course, are solutions. Okay. The sugar in a soda drink would be an example of a solute in that solution because it occurs in the lesser amount. The water, again, is in the larger amount. Okay. Another example, okay, going back to the soda drinks, right? Carbon dioxide. Okay, they are, there's bubbles, right, in the soda drinks. Carbon dioxide is a solute in soda drinks. It is there in lesser amount than the water, which is the solvent. Okay, so let's turn things around. Okay, in a salt water solution, water is there in the greater amount. So water is the solvent. In soda, again, who's in the greater amount? Water. So water is the solvent in that solution. All right. Next slide. Nature of solutes in the solution. Let's focus on the solutes. Okay. When we're talking about a solution, the solute in a solution is spread evenly throughout the solution. Think of any of those examples that were on the previous slide. Okay. You cannot separate the solute from the solvent in a solution by filtration. And you're all familiar from lab with the process of filtration. However, the solute in a solution can be separated by evaporation. Think about a salt water solution. If you take a glass at home, okay, and dissolve table salt in it, and then leave it out on the counter for a period of time, depending upon how much is in there, okay, the water will evaporate and you will see the crystals of your sodium chloride, your salt, come out. So the solute in a solution can be separated by evaporation of the solvent. The solute is also not visible in a solution. The solution, when you look at it, appears to be transparent. If your solute is colored, then it may give a color to the solution. Types of solutes and solvents. Well, solutes and solvents can be solids, liquids, or gases. The solution that forms when you mix a solute in a solvent has the same physical state as the solvent. Some examples. Okay. Air. Air is a solution. Oxygen gas and nitrogen gas mixed together. It is a gas solution. The solute and the solvent are both the same. They're gases. Let's think soda. Let's use that as an example. The soda. Okay, right here. Who do we have? Well, water is the solvent. And let's take one of the solutes that we talked about. Let's take carbon dioxide. For example, carbon dioxide gas is dissolved in the water. So we have gas dissolved in the liquid solvent. Right? Think about what soda looks like. The solution that forms has the same physical properties as the water. All right. Seawater. Okay. Seawater is sodium chloride and other things in water. All right. Think of what it looks like. It's a solid, that's sodium chloride, table salt, right, dissolved in water. And your solution, your seawater, it has the same physical properties as the solvent. Now, typically when we think about solutions, we think of the solvent as being water, but again, it does not have to be. The solvent can be a gas, such as in air, right? And the solvent can actually be a solid, as in brass. All right, brass is a homogeneous mixture of copper and zinc, so it is a solid solution. Water as a solvent. This is what we are going to focus on primarily in this chapter. So let's just start with water. It's the most common solvent. So that's why we're going to study it. Water. What do we know about it from our study of covalent molecules in an earlier chapter? It is a polar molecule. Let's refresh ourselves with the structure of water. Water's formula: H subscript 2 O. 2 hydrogens covalently bonded to a central oxygen. That oxygen is more electronegative than the hydrogens and therefore possesses a partial negative charge, causing each of the hydrogens in the water to take on a partial positive charge. So we have a polar molecule. We have a hydrogen covalently bonded to an oxygen. We are perfectly set up for hydrogen bonding. Bring in another molecule of water with the same polarity, and we have the capability, because we have that hydrogen bonded to an oxygen, we have the capability for a hydrogen bond. If you don't remember what a hydrogen bond entails, go back to our previous chapter on covalent compounds and review. Hydrogen bonds. Let's pull in some more molecules in our sample of water. Hydrogen bonds attract polar water molecules to one another. Remember, hydrogen bonds are strong. They're one of the strongest intermolecular forces. Every single one of these hydrogen bonds would have to be broken before we could take liquid water and convert it to the gaseous state. Well, we already know that water is a major component in our bodies. The average adult, as a matter of fact, is about 60% water by weight. Infants, a little bit different. They are actually 75% water by weight. 60% of that water comprises the intercellular fluid, that is in the cell, and 40% of the water that's in the body comprises the extracellular fluid, that's the fluid outside the cells, the plasma in the blood, the interstitial fluid. It's that extracellular fluid that carries nutrients and wastes between the cells in the circulatory system. More on water in the body. So during the course of a day, right, in your daily activities, you lose approximately between 300 and 1,500 milliliters of water each day. If you lose too much, dehydration occurs. All right, so what are the markers? Dehydration is going to occur if there's a 10% net loss in body fluid. Of course, for infants, it's going to be less. Infants, it's between 5 and 10% loss. 20% loss, and it becomes fatal. Water is continually being replaced by liquids that you drink and also by the foods that you eat. Your body has the ability to pull the water out of the foods you eat, and also from metabolic processes that are just going on in your body, and the side product of those metabolic processes is in fact producing water. So, solutions. How do solutions form? Let's look at the solution process, step by step. When a solution forms, and remember, okay, there are two parts to the solution. There's the solute, the substance that's in the lesser amount, and the solvent, the substance that's in the greater amount. And we are focusing, again, let me remind you, we're going to focus on solutions that are in water. So the water is the solvent, the substance in greater amount. All right. So when a solution forms, the solute particles have got to break apart, break away from other solute particles, and then move into your solvent. At the same time that your solute particles are breaking away from other solute particles, the solvent has got to allow solute particles to come between the solvent particles. In order for this to happen, there has to be an attraction between those solute particles and solvent particles, or else they are not going to mix. Recall those intermolecular forces from our previous chapter. Those were the forces of attraction between different molecules rather than the bonding forces within the same molecule. There were 3 of them, and they varied in terms of their strengths. Dipole-dipole attractions, if you do not remember what they are, review. Go back and review. Hydrogen bonds, remember they were the strongest type of attraction. That's what we have going on between water molecules. Okay. And then we had those very weak dispersion forces. Everything has the dispersion forces. Doesn't matter whether they're polar or non-polar. All right. So again, go and review these 3 types of intermolecular forces. Okay. So the solution process, keeping in mind that molecules are going to have either the hydrogen bonds, the dipole-dipole interactions, along with dispersion force, because every single atom and or molecule has those dispersion forces. Okay. In addition to those, we also see either hydrogen bonding or dipole-dipole, or just dispersion. All right, so keeping those in mind, the solution process. Let's continue with it. A good rule of thumb for predicting whether or not something's going to dissolve is like dissolves like. And you may have heard of this before. What does it mean? Substances that have similar intermolecular forces are going to form solutions. And substances with different intermolecular forces going on do not. It's as simple as that. Ooh, I'm going to come back, hopefully, and see if I can correct this, because my picture keeps being going over the some of these illustrations, so I've got to correct that. Maybe I'll take them off and put them as handouts. Okay. Or put it up without me in it also. I have to solve that. Apologies for that. Okay, so here we go. This is exactly what we said. Like dissolves like. Solutions form when these kinds of forces are similar. Okay, so solvent, we have the solvent, we have the solute. Notice there's different shapes, so that's all there is there. And there are intermolecular forces going on between the solvent molecules. Okay, that's what's holding them together. Over here on the solute end, we have some sort of forces holding the solute molecules together. All right, intermolecular forces. Okay. What did we say has to happen in order to end up with a solution? Here's our solution with the solvent solute. These forces have to break, right? These attractions between solute molecules have to break apart. The ones here have got to break apart. And we have to form a new attraction between the solvent and the solute, our solution. The only way this is going to happen is if the forces holding the solvent together and the forces holding the solute together are similar. Like dissolves like. If they are not similar, if these forces, these intermolecular forces holding the solvent together and those that are holding the solute together are different, we are not going to see, you can X this guy right out here, we're not going to see our solute and our solvent forming a solution. Okay. Like dissolves like. More on our like dissolves like. This means that nonpolar solutes, and you know who's nonpolar, okay? No polar bonds, okay? No dipole moment, no permanent dipole. We talked about it in a previous chapter. If you don't remember, you need to go back and review. Nonpolar solutes are going to dissolve best in nonpolar solvents. Why? Because nonpolar solutes are going to have the same sort of intermolecular forces holding them together as the nonpolar solvents have. So Let's give you some example of some nonpolar solutes. Fats, steroids, waxes, all nonpolar solutes. They're going to dissolve best in nonpolar solvents: benzene, hexane, toluene. And polar and ionic solutes are going to dissolve best in polar solvents. Some examples of polar and ionic solutes and polar solvents: inorganic salts, any of those ionic compounds, inorganic salts, that's what we're talking about, okay? And sugars. Sugars are polar. They have polar bonds. So inorganic salts and sugars, they're going to dissolve in polar solvents. Who are some polar solvents? Water, small organic molecules, and acetic acid. Solutions with ionic and polar solutes. All right, so let's start up at the top of the slide. Okay. In ionic solutes, let's take our go-to example, such as sodium chloride. Remember when we talked about sodium chloride, that ionic compound, right? Ionic compounds have strong solute-solute attractions between the sodium ions and the chloride ions. When sodium chloride is placed in water, a process called dissolution begins as the surface of the ions comes in contact with the water. All right, so what do we see in this illustration here? Well, this is a crystal of sodium chloride. All right. Remember, sodium chloride has the sodium ions and the chloride ions, the sodium ions being the small blue and the chloride ions, right? Okay, they are being held together by very strong electrostatic attractions between the positive sodium ion and the negative chloride ion, right? Dissolution is beginning here at the surface when our solvent, the water, comes in contact with the ions that constitute that crystal, okay? So our water, let's show it out here. Remember, partially negative oxygen right here, partially positive hydrogens. The oxygen atoms in the water, right, attract the positive sodium ions. And these partially positive hydrogen atoms in other water molecules are going to attract the negative chloride ions. All right, so that's what's happening at the surface of our sodium chloride molecule here. Okay. Again, dissolution involves that partially negative oxygen right here in our water. It's going to attract the positive sodium ions that are in the crystal. Okay. And then we see other water molecules, right, where the partially positive hydrogens are going to be attracting the negative chloride ions. So it's that opposite charge attraction. Okay, so here it is. Here are our players, okay, in this whole process. We have our water, which is our solvent. We have our sodium chloride right here. Okay, and so I've separated out. Here's the sodium ions. They're positively charged. Our chloride ions, which are negatively charged. Okay, so what we're seeing here is the dissolution, that's the term that we use, of a sodium chloride crystal in water. Our polar water molecules, right, surround individual ions, pulling them from the crystal surface where everything begins into the solution. Okay, so here they're starting at the surface, the opposite attraction, right, between the oxygen, right, and the sodium ions, between the hydrogens and the chloride ions, and the water molecules are pulling the ions into solution. Notice how they're arranged. Here's a sodium ion, positively charged. Notice how the waters arrange themselves with the partially negative oxygen around those sodium ions. Notice how the water molecules arrange themselves around a chloride, the partially positive hydrogens being attracted to the negative charge on the chloride. Okay, the oxygen atoms point to the positive ions. Here they are. And the hydrogen atoms are pointing to the negative ions. The attractive forces between water and the sodium and the chloride ions are what pull the ions into solution until every single one of these ions in the crystal is surrounded, just as we see here, by the water. Formation of a solution. Another pictorial of what is going on here. Here's our sodium chloride crystal. That's our solute. In our solvent, which is water, our water molecules pull and surround, hydrate, as we say, okay, hydrate the ions by surrounding them and pulling them into solution. Okay, when all is said and done, there will be no solute left. There will simply be ions hydrated by water. Okay. Next up, now that we understand the process for dissolution of a polar compound, an ionic compound in water, we need to be able to represent that, because we don't want to be drawing those pictures all the time to show what's going on. So you need to know how to write an equation for the formation of a solution. So let's take that sodium chloride as an example. When solid, so remember we learned in a previous chapter, right, how to denote the physical state of something, right? An S, right, lowercase s, in parentheses behind something indicates that we have a solid. So when solid, sodium chloride dissolves in water. Right? We don't have to draw those elaborate pictures as we had on the previous slides. All right. We can write a reaction to depict the formation of the solution. How do we do it? Here we go. We write our compound and the state of that compound. So sodium chloride we're talking about, it is a solid state. All right. What are we doing with it? Well, we are taking it, so we use an arrow, a reaction arrow, right? And we're dissolving it in water. So we place the water over the arrow, okay? Bounce it on in there. And what's happening on the other side of the arrow, we show what happened in our pictorials. Our water, remember, hydrated the sodium ions and the chloride ions. It pulled them apart, so we no longer have that solid, right? We have hydrated ions. So we have sodium ions that are surrounded by water. How do we show that? Well, we say that it's aqueous, okay? AQ in parentheses means that our sodium ion is totally surrounded by those water molecules, as we showed on the previous slides. And what's happened to the chlorine or the chloride atom, chloride ions? Well, they too have been hydrated, surrounded by the water molecules in the manner that we showed on the previous slides. So how do we show it in an equation? It is the chloride ion, there it is, with that AQ in parentheses, that's telling us the state. It is aqueous. It is in solution, which means, right, what's the solution? It's water. Okay, and that means that that chloride ion is totally surrounded, as in our previous slides, by water molecules. All right, the hydrogens, the partially positive hydrogens surrounding that chloride ion, or the chloride ions, all of them. All right, so we begin with a solid, okay, which is our solute, and we place it in water. Okay, so that's what the water over the arrow is showing. And over on the other side of our equation, we are showing the separation of the ions in water. All right. More on our solutes. What else can we tell you? Well, solutes in a solution are classified into two general categories based on their ability to conduct an electrical current. Solutes are categorized as either being electrolytes or non-electrolytes. So two general categories. Let's look at them both. Beginning with electrolytes. What are the properties of electrolytes? They are substances, so they're going to be solutes, all right, that form positive and negative ions in water. And they have the ability to conduct an electrical current. That means that if you have a setup that we will look at shortly, okay, and you have solutes that are, or a solute that is an electrolyte, one that forms positive and negative ions in water, it will cause electricity to flow and a light bulb will light up. All right, so it'll conduct an electric current. So electrolytes, who are they usually? They are water-soluble ionic compounds, such as sodium chloride, right, and some of those other ionic compounds that we learned about in a previous chapter. They are electrolytes. And then we have the non-electrolytes. Non-electrolytes dissolve as molecules only. No ions are produced from a non-electrolyte in water. So since there are no ions being produced, non-electrolytes do not conduct an electric current. An example, glucose. Glucose is C6H12O6. It is a solid. It is polar. It's a polar compound because it has oxygens bonded to hydrogens. It's not ionic, it's molecular. It will dissolve, notice the equation, it will dissolve in water. We're showing that over here, right? That little AQ means that this glucose molecule that was a solid is now hydrated, surrounded by the polar water molecules. Okay, but notice, distinctly different than our sodium chloride, there are absolutely no ions in solution. Right, so no ions will not conduct an electrical current. Notice I do not have that light bulb here lighting up. Okay. Electrolytes versus non-electrolytes. Let's start at the top. Okay, let's show you a setup, okay, to be able to distinguish between a solution that contains electrolytes versus a non-electrolyte. Okay, so we show the solution being tested. Okay, we have some electrodes that we dip into the solution. Okay, and a light bulb attached, and we have we're hooked up to an ammeter, and notice a battery. Okay, so when we complete the circuit, okay, this ammeter here, all right, is going to measure the flow of electrons. Flow of electrons is simply the current, okay, through this entire circuit. All right. So what happens? Well, if that ammeter, okay, notice right now that arrow on the ammeter is not at 0, it is actually measuring a current. Okay, if the ammeter measures a current, what's happening here? Our diagram is showing that the bulb is lighting up. The bulb glows, and that means the solution is conducting electricity. Okay. All right, charges are required, remember, for electricity to flow. All right, if the ammeter fails to measure a current and this bulb does not glow like it's glowing here, that means the solution is not conducting. Okay, so those are the two possibilities. All right. If the ammeter is in fact measuring a current and that bulb glows, that means, again, charges are present. If the ammeter fails to glow, right, that means that you're not measuring a current, and that means that there are no charges present. So electrolytes have charges present in solution, non-electrolytes, none. Charges are necessary to conduct electricity. Electrolytes are going to conduct electricity, non-electrolytes not. In addition to those two general categories, electrolytes, non-electrolytes, for solutes, we can take that electrolyte category and we can split it into two types of electrolytes: strong electrolytes and weak electrolytes. Let's begin with strong electrolytes. Strong electrolytes are 100% ionized in solution. Who are strong electrolytes? Salts. Salts like sodium chloride and other ionic compounds, right? Those are our salts. When you dissolve them in water, they are strong electrolytes. They are 100% ionized. That means we no longer have the salt, we have ions on the other side. 100%. No salt remains. For instance, let's go back to our go-to salt, sodium chloride. Okay? It is a solid ionic compound. It is a salt. It is a strong electrolyte, because when we take our sodium chloride and we dissolve it in water, let's bring that water in there. This is how we showed that equation, remember, for the dissolution. What happens? The water pulls apart the sodium chloride solid and totally hydrates it. That's what this means over here. So notice I have ions. That's all I have. No more solid compound. 100% ionization. Strong electrolyte. Let's look at another one. Okay, another example of a salt. Let's take calcium bromide. All right, this is a good place to review your naming, okay, and also what this formula means. Okay, it is a metal and it is a nonmetal, which means it's an ionic compound. So we're talking charges here, right? Remember, charge on calcium comes from its group number. Charge on our bromide ion also comes from where it is in the periodic table, right? So it is in group 7, right? And so it needs one electron to become like a noble gas. It has a -1 charge, okay? So charges have got to equal 0, so we crisscross, right? Calcium plus 2. All right, so when we take calcium bromide, which is an ionic salt, and we dissolve it in water. So let's show the equation for the dissolution. Let's put that arrow there. Let's bring in our water. Over the arrow shows we're dissolving it in water. What's the water going to do? It is going to hydrate. It is going to totally surround the calcium ions, calcium plus 2, right? And the bromide ions, and it's going to pull them into solution, right? Watch the difference, okay? Calcium plus 2, right? Because that's what this is here. Okay. And bromide, Br minus Aq, totally surrounded. But I have in my equation 2 of them. Why? This is a chemical reaction. We have to balance everything that's on the left with everything that's on the right. So we have to follow the rules for balancing equations. If you did not master that, you need to master it. So there's a lot of things that we're depending upon you having mastered here. Knowing what the charges of the ions are here, being able to separate it appropriately, and then balance the reaction, right? We got one calcium here, one here, right? That's really a calcium plus 2, even though we don't show it, right? 2 bromide ions here. Remember, that's really a negative charge, but we don't show it in the formula, right? And so we have to have 2 over here. Here we only have 1, right? And again, we know that that's a plus charge and a negative charge there, right? They're ions because it's an ionic compound. Metal, non-metal. Right, so if you didn't master a lot of this stuff, you have got to go back and make sure you have it. Okay, that's your foundation that we're building on. Okay, what else? Let's see. Who else is a strong electrolyte? Well, strong acids, it turns out, are strong electrolytes. And a couple chapters down the line, we're going to look more into the strong acids. I'm going to give you one example right now of a strong acid and show you how it is a strong electrolyte because it 100% ionizes. Okay, strong acids, when we place them in water, just like the salts, give us 100% ions. Okay? So an example, HCl. Okay? HCl gas. When we take HCl gas and we dissolve this gas in water, we get 100% ions. Okay, we're going to end up with that same issue again. We get H3O plus, and who's hiding under here? Well, it's Cl minus AQ. Okay, so let's see if I can do this. I don't know if I can see. Ooh, look at that. It's really hard to write with this. Cl minus. Okay, and I wish I could type. That would be really good. All right. Again, these are learning curves. I'll learn how to do these things. Hopefully next time, next PowerPoint AQ. Oh my gosh, this is terrible. But at any rate, okay, so it's plus Cl minus AQ. And again, it's only one, right? All right. So a little bit different for strong acids. Notice what's happening. That H plus that we have here, right, is glomming onto the water to give you this H3O plus. Okay, but that AQ means the same thing. It means that water molecules are in fact surrounding entirely hydrating that H3O plus. Okay, and the AQ here means that they're glomming around that chloride. Okay. All right. So strong electrolytes. Again, what does it mean to be a strong electrolyte? Those kinds of solutes, totally 100% ionized in solution. Okay. All right. So the second type, okay, subtype of electrolyte is the weak electrolyte. All right. A weak electrolyte, all right, how do they differ? All right. Well, when you dissolve a weak electrolyte or a solute that is a weak electrolyte in water, most of the solute at the end of the solution process exists as molecules in solution, not ions. So how are we going to show this? The fact that most of the solute, when we dissolve it in water, exists as molecules, and very few particles are producing ions. So you have very few ions in solution. You have mostly molecules. How are we going to change our equation to show the difference? Follow closely. Let's take an example of a weak electrolyte. So right now you're going to have two examples of weak electrolytes. We're going to have to tell you such and such is a weak electrolyte so you know what to do to draw an equation. All right, so hydrogen fluoride is a weak electrolyte. Okay, so this is how the equations are going to differ. When you have a weak electrolyte and you're writing an equation for dissolution, remember how we were putting the water over the arrows? We no longer put the water over the arrow. We write it on the reactant side as a reactant. So our solute, hydrogen fluoride, and we're adding our solvent, water. Okay? Arrow to show what are we going to get. All right? That's what we usually do. Well, remember we said we're not going to get 100% ions, right? Most of the solute is going to exist as these molecules over here, right? The hydrogen fluoride. And we're not going to get too many ions on the other side, all right? So how are we going to show that? Here's another secret. You're going to put a double-headed arrow, okay? Double-headed arrow, okay? So this is one difference, right? Our water's coming over here on the reactant side, right? Plus water, not over the arrow. And we're going to use a double-headed arrow. All right? So that means that we're going to get some of these ions on the other side. Okay? We're getting some water glomming onto that H plus, okay, to give us H3O plus. And we're getting some fluoride ion, but not too much, so imagine that. So we're getting some, so that's what the arrow going in this direction is telling you. The arrow going in the opposite direction says, yeah, but most of it goes back and gives us what we originally had. Okay? So the form of the equation for the dissolution is telling you that that is a weak electrolyte. Okay, that double-headed arrow, okay, the position of the water tells us a lot. Let's give you one more example, okay? So hydrogen fluoride in it is in fact a weak acid, and again, we're going to see more of that hydrogen fluoride in a chapter to come that covers acids, all right? Okay, let's give you another one. This is ammonia, NH3. We've been introduced to it before when we were doing molecular formulas, right? Lewis structures, that's ammonia. It's a covalent compound. Because we have hydrogens bonded to nitrogens, we also have the possibility of hydrogen bonding, right? So it's a polar compound. When we take ammonia and we dissolve it in water, okay, it's a weak electrolyte. So how are we going to show that most of that ammonia stays in the molecular form? Okay, we're going to incorporate a double-headed arrow. Okay, so let's put our double-headed arrow. Means we're going to get some of what's on the other side, but most of it's going to return to this form over here. All right, so this one's a little bit different. Okay. We end up with our ammonia picking up the hydrogen, so it's NH4 plus, right? And the other one here that we can't see that's hiding under here is OH. It's our hydroxide ion. Okay, OH minus. Okay. And then there's the AQ. There. Writing comes out a little bit better than the printing. Okay. Alrighty. So we get some ions. Alright. But most of it returns. Okay. So we get ion formation, but most of them recombine and give us back our original, okay, molecular form. Okay. And ammonia turns out as a weak base. So when, again, we're going to see more on weak acids, weak bases, being weak electrolytes in our chapter to come on acids and bases. Okay. So I think the last thing that we'll do here, I think this is a good point to end, and this is enough material for the quiz, all right? The last thing that you're going to do here is you're going to try to classify the following substances as electrolytes or non-electrolytes, okay? So let's see here. Here are our substances that you're going to go through. Pure water, okay. Tap water, okay. Keep in mind, I'm going to give you a little bit of a hint here. Tap water, remember, is not pure water. There are things dissolved in our tap water, okay, that comes out of the faucet. Just a hint, okay. Number 3 would be a sugar solution. So you're going to do some thinking here. Sodium chloride solution. Hydrochloric acid solution. That is HCl, all right. Lactic acid solution. Lactic acid, I'm going to tell you, is a weak acid. Okay, so I've got to give you some information on it. Ethyl alcohol. Ethyl alcohol. Ethyl alcohol is, let's give you the formula for this. Okay, so you can see what it looks like. It is CH3 CH2. Okay, so remember you can do the Lewis structure for this. Okay. All right, remember each carbon has 4 bonds to it. All right. Remember, right? Okay, OH. So now that you have that, you're going to be able to tell, right, what it is. Okay, is it molecular? Is it ionic? All right, you need a little bit of that information. And how about a pure sodium chloride? Pure sodium chloride would be solid sodium chloride. That's what we're talking about here. Okay. All righty. Let me just see. Okay. So, answers to our electrolytes. Okay. Give you a little bit of time there to go through. Okay. That's what you want to do. You want to make sure that you get all of those. Take the time. All right. Tap water. Tap water, remember I said, has got some ions in it. All right. Is it 100% ions? Yeah. Any ions, right? Any substances in there, it's going to be an electrolyte. It's going to be weak though. Okay. It's going to have some ions, not 100%. All right. Sodium chloride solution, 100% ions, right? It's going to be an electrolyte. HCl, right? Strong acid, we said, it's going to be an electrolyte. Lactate solution, remember I said it's a weak, right? It's a weak acid, so it's going to be a weak electrolyte, right? Non-electrolytes, pure water. Absolutely no ions, okay? Sugar solution, no ions. Remember we talked about sugar, right? Glucose, okay, non-electrolytes. And the ethanol solution, absolutely no ions, right? It's a molecular compound, all right, similar to that sugar, okay? And then pure sodium chloride, just plain old solid sodium chloride. Remember, doesn't have ions, right? They're all attracted to one another. They're not free, so it's not going to conduct electricity, so it'll be a non-electrolyte, okay? Now, there are other problems in your textbook. Make sure that you do the problems. If you missed anything on this video PowerPoint, make sure you go back and yeah, you can listen to me again, okay? So hope you enjoyed this, and if you have any questions on any of the material for week 8, please message me on Canvas. We can always try to set up, if I can't answer through Canvas messaging, we can always try to set up a Zoom, an individual Zoom session. Okay, now I've never done that before. You guys probably have not either, so we will learn. Okay, so enjoy, and this is how far the quiz will cover. All right, pay attention to the announcements. The announcements tell you exactly what I'm going to be asking on the quiz, the 25-point quiz, come this Sunday. All right, have a good rest of the day.